Welcome, interconnected viewers, to Science and Spirituality. Last week on our show we discussed some of the amazing phenomena and predictions of quantum physics. For example, superposition could mean that a particle can be at two or more places at the same time. Also, distant entanglement is where objects which are separated by practically infinite distances act in a unison. This is if one changes, the other responds instantaneously with zero time delay. While many quantum technologies have already been implemented for nearly 100 years, a debate has continued as to how we interpret the quantum theory. The idea within quantum theory of replacing particles with waves of discrete or quantized frequencies akin to the vibrations of a guitar string was quite revolutionary. Pretty soon, these new ideas were enhanced by mathematical tools. In 1925, Erwin Schrödinger came up with his famous wave equation, which went on to become a key tenet for much of modern physics. Within a few years, physicists were able to explain wide spectra of previously not understood atomic and chemical reactions. But the wave of matter, this quantity, the wave function derived by Schrödinger equation, what exactly does it describe? This central puzzle of quantum mechanics remains a potent issue to these days. Max Born had the insight that the wave function should be interpreted in terms of probabilities. For example, if we measure the location of an electron, the probability of finding it in a given region depends on the intensity of its wave function there. No one knows where it comes from. It just works. Soon physicists realized that any observation or measurement performed on a quantum object converts it into a classical body of matter. In fact, any quantum object can appear as a wave or particle, depending on the given circumstance. Albert Einstein, who actually noticed this phenomenon first, was concerned that this idea posed a danger to his dream of an orderly universe. Niels Bohr pointed out that because human perceptions, senses, and powers of communications are rooted in the classical realm of physics and its corresponding laws, it is impossible to perceive quantum phenomena in any other way than through the classical phenomena. So some kind of medium was necessary to translate quantum phenomena into the classical language of physics, some kind of measuring standard, such as click in a particle counter, or a light detector, or a photographic plate exposure. This view is the essence of the Copenhagen interpretation of quantum mechanics, of which Niels Bohr was the main proponent. The Copenhagen view assumes that particles do not have set properties before they are observed. Instead, particles are described by wave functions representing the superposition of many mutually contradictory possibilities. For example, particles can simultaneously exist in many places, and the coin can be both tail side up and head side up at the same time. However, as soon as we look at them or measure them, they become classical objects, randomly choosing one of the possible states. So in the 1920s, physicists explain away this strangeness by postulating that the wave function collapses into some random but definite classical outcome whenever someone made an observation. This add-on had the virtue of explaining observations but left the theory incomplete because there was no mathematics specifying what constituted an observation. Einstein did not agree with this interpretation, which fundamentally builds in randomness in the physical laws of nature. He expressed his preference for deterministic universe with the often quoted remark, "I am convinced that he does not throw dice. He means God." Niels Bohr replied, "Albert, stop telling God what he must do." On the other hand, the mathematics of quantum mechanics pictures the world very accurately, and it has to be emphasized that there was no experiment that was in disagreement with the prediction of quantum mechanics up to now. And quantum mechanics agrees with our observations up to many decimal places of accuracy. But when it comes to in-depth understanding, many physicists are still unclear.
Quantum mechanics is a mathematical description, a purely abstract mathematical description that apparently mirrors nature perfectly. It's every time we make a prediction from quantum mechanics and we go out and learn a new experiment to do, we confirm that that's the behavior that we see. And so it's a theory that thus far completely describes everything we've been able to observe in nature and in the universe. And it's a mathematical framework by which to predict and describe behaviors.
And so physicists were being driven into a situation where they had to be opportunists. The only way they could possibly explain some things was by using these ideas and relying on the mathematics rather than on any philosophical or physical idea. But the funny thing is that some of these physicists were very philosophical in their approach. So Einstein was essentially a realist, although many of his ideas changed our understanding of reality very radically.
Eventually, the great scientist Albert Einstein was left alone with his dream of a theory of an orderly universe. Mainstream physicists move on with their know-how to unravel the secrets of nuclear energy. When we return, we will hear about an intriguing alternative interpretation of quantum physics. Stay with us to find out more about it. This is Science and Spirituality on Supreme Master Television. Welcome back to Science and Spirituality. Although quantum mechanics is often described as inherently random and uncertain, there is nothing random or uncertain about the way the wave function evolves. The problem is how to connect this wave function of possibilities with the seeming classical particle appearance of an observer's experience. In 1957, Hugh Everett, a graduate physics student at Princeton University in the United States, thought about this problem using the example of a double-slit experiment, so let us follow it closely.
Particles, such as electrons or photons of light, do something strange. When fired at two slits, they create an interference pattern like waves when they should make two bands like matter. Even when fired individually, a single particle headed towards a double slit will split, proceed to pass through both slits, and then interfere with itself to create an interference pattern like a wave. This causes it to go through both slits, neither the first and the second. However, when measured, something strange happens. Rather than the previous interference pattern, the pattern of an observed particle resembles that of matter. The mere act of observing which slit is chosen actually causes the particle to go in only one.
Everett's creativity had helped him glimpse an extraordinary possibility. What if there were not one, but two electrons running through those separate slits? But then, why would the act of analyzing the intensity of interference pattern measured at the wall indicate only one electron passing through the double slit? The answer is that the other electron existed in another universe. When there are two possible paths for an electron to pass through these two slits, there are actually two electrons going along these separate paths, both in parallel universes. Initially, those universes occupy the same space, but once a measurement is made to decide which path the electron took, the two electrons in both universes become independent. This is the so-called many worlds interpretation of quantum mechanics. In this view, the wave function never collapses upon measurement, but continuously evolves in time with the theory being deterministic like in Newton's classical mechanics. Everett's brilliant insight was his quantum theory interpretation, which negates the need for wave function collapse. This is also consistent with observations. The wave function, initially describing one classical reality, gradually evolves and describes the superposition of many such realities taking place in the many worlds. These measurements or observations are like a filter, simultaneously selecting the outcome and, in a sense, selecting the universe. This is because anything that can happen will happen in one or the other universe. Hugh Everett wrote a paper about the ideas, which was published, but it was not well received by the scientific community. He left academia and became a very successful industry mathematician. Today, we observe a clear upward trend in the interest and acceptance of Hugh Everett's ideas. Cosmologists and quantum computing scientists now very much appreciate his many worlds interpretation. Any successful efforts in building a quantum computer will doubtlessly strengthen further this view in the future, when realized this kind of computer will be many times faster than the computers we know today. Quantum mathematicians appreciate that in Everett's many worlds interpretation, the wave function does not collapse, so the quantum world becomes much easier to work with. Many prominent physicists have agreed with Hugh Everett's interpretation and theory, although some have expressed reservation with the name many worlds. Famous proponents of this line of thinking include Stephen Hawking and Nobel laureates Murray Gell-Mann, Richard Feynman and Steven Weinberg. Why is the many worlds theory now being embraced? It could be for many reasons. Today's science is more open to the idea of parallel universes. A similar idea was also proposed in cosmological inflation theory or string theory. Without doubt, science has been more receptive to imaginative ideas. Another reason is that new experiments have demonstrated quantum superposition extending beyond electrons and into the worlds of even larger systems. Interference patterns were observed in a double-slit experiment with the large Fullerene molecule of carbon C60 called a buckyball. However, the most important shift towards the recognition and acceptance of the many worlds interpretation was the discovery of a process known as decoherence, which answered crucial questions that Everett's work left unanswered. In short, it addresses the question that if those parallel universes exist, then why do we not perceive them? The breakthrough came in 1970 with a paper by H. Dietersee showing that the quantum nature of the wave function itself gives rise to a phenomenon which he named decoherence. This idea was later developed by Wojciech Żurek's research. Indeed, quantum superposition can be observed as long as the object is isolated from the rest of the world. Otherwise, the quantum superposition of electronic states loses coherence and chooses one of their possible classical states through being bombarded by photons, thermal vibrations of atoms, or other random interactions with their environment. So this is the coherence, the dissolution of the quantum superposition state, which simply produces a natural effect that looks like a collapse of the wave function. But should we really believe the many worlds interpretation? It depends on one's perspective. We can have the outside view of a god physicist studying the mathematical equations of a landscape of universes from high above, or the inside view of a human observer living in one of the universes. From the god physicist's perspective, Everett's many worlds interpretation is the simpler and more transparent concept. There is only one wave function, and it evolves smoothly and deterministically over time without any kind of world splitting or parallelism. From the human insider perspective, it looks like a world which continuously splits and appears random. If you prefer the human insider perspective and explanation, you would probably live with the concept of separateness of the quantum and classical world and be content that you do not have to worry about the other universes. But if you prefer a simple and purely mathematical theory, then you would choose the many worlds interpretation. The problem is that if we dismiss the many worlds interpretation because we can't observe everything, or because it seems too strange, we risk missing true discoveries in science. After all, not long ago, in 1920, the Shapley-Curtis debate was taking place about whether or not any other galaxies existed outside of our Milky Way galaxy. By the standard of the time, other galaxies seem as incredible as parallel universes appear to some of us now. Of course, we know that there are billions upon billions of galaxies outside our galaxy. Thus, once again, science is expanding to acknowledge the limitation of our human perception in understanding the physical universe, which reveals itself to be grander and more sophisticated than we could ever imagine. At the same time, science is becoming closer to spirituality. Thank you, viewers, for watching today's edition of Science and Spirituality. Words of Wisdom is up next, right after noteworthy news on Supreme Master Television. Be interconnected. See you next time in this universe or another.